we're going to look at these limits at infinity for a variety of types of functions. And I want to start with a type of function that should be a little bit familiar to us, which is rational functions. If you remember from previous classes, a rational function is going to be a function where we have a polynomial divided by a polynomial. So this function f of x here is a rational function because the numerator and denominator are both polynomials. So we're going to look at what happens with this function as we plug in larger and larger values for x into this function. So I want to look at what's going to happen with the numerator and denominator separately first, and then kind of put it together and see if we can figure out what's going to happen with the function as a whole as x gets really big. So looking just at the numerator, if I plug in a really big number for x, and by really big, it's kind of an arbitrary choice. We could say 1,000 is a big number or 1,000,000 is a big number. Well, the bigger number that I plug in for x, let's say 1,000,000, when I square it, this is going to have a really big impact on the value of the numerator, where this term right here, I'm not squaring it, it's just say 1,000,000, isn't going to have as much of an impact, and this term here is going to have very little relative impact to the other terms. So realistically, as x gets really big, the value of the numerator is going to be dominated by that term, that 6x squared term. So this, if I plug in 1,000,000, this is going to be 6 trillion, this is going to be 2 million, and this is going to be 1. Well, when we're talking trillions, the 2 million and the 1 have very little impact. In the denominator, same idea. When we plug in a really big number, this is going to have a much bigger impact than the other terms. So I know those are going to have bigger impacts, the 6x squared and the 2x squared, because the degree on the x is bigger. So what we can do is we can say the top is going to behave like the function 6x squared. As x gets really big, the difference between 6x squared and the rest of this is going to be minimal. So f of x, as x gets really big, is going to be about the same thing as 6x squared over 2x squared. All right, and the idea is we're looking for what's going to dominate or have the biggest impact on the value of the numerator and the denominator. Well, using algebra, this expression is the same thing with the x squareds canceling. It's the same thing as just 3. So what we're saying here is as x gets really, really big, this function is going to behave like this function, and that function is identical to the number 3. So we can say that this limit is going to be 3. You may remember using an idea like this with horizontal asymptotes with rational functions. And we're going to connect these limits at infinity with horizontal asymptotes later. But you probably had a rule where you said, okay, we can take the leading coefficient of each of these and divide them to figure out what the horizontal asymptote is going to be. And that's exactly what we're doing here. All right, if we look at a few other examples, the first example here, when we plug in large values of x, the numerator, the 6x cubed is going to be the most impactful. It's going to dominate the value of the top, and the 10x cubed is going to dominate the value of the bottom. So this is going to behave like the function 6x cubed over 10x cubed. And I'm going to use limit notation here because I'm not plugging in, and I want to clarify we can't actually plug in infinity because infinity is not a number, but we're not removing x from our expression yet, so this is going to behave like this. And since it's going to behave like that and the x cubes cancel each other out, this is going to be 3/5. Okay, now the other two examples, we've got something a little bit different going on here. So in the next one, this is going to behave like 6x to the 4th over 10x squared. So let's rewrite that. Well, this time when we do some canceling, the x squared in the denominator is going to cancel with 2 of the x's here, and we're going to get x squared left in the numerator. And so this is going to behave like 6x squared over 10. Well, as we plug in larger and larger values for x here, The 10 is not changing in the denominator, so we're plugging in really big numbers and getting a really big number in the numerator, and the denominator is staying constant. So when we take a really big number divided by just some constant, we're going to get a really big number, and this limit is going to be infinitely big. Technically, this limit does not exist, but we want to use infinity or negative infinity if appropriate, so that we can be a little bit more descriptive of why that limit doesn't exist. The last example here, we are going to have a function that's going to behave like x over 3x squared. So this is going to be the same thing as the limit as x approaches infinity of x over 3x squared. This time, when we do some canceling, we have an x left in the bottom. So as we plug in values for x here that are getting really big, we have 1 divided by a really big number. Say we plug in 1,000,000, 1 divided by 1,000,000 is a really tiny number. It's really close to 0. So when the denominator is growing really big while the numerator stays constant, this is going to be 0. Okay, so a constant divided by a really big number is going to be 0. So we've got 3 different cases here, and the difference between these 3 cases is the degree of the largest degree term in the numerator and denominator. So in the first one, we looked at the x cubed terms here, and the x cubes canceled each other out because they had the same degree. In the second one here, we had x's left over in the numerator because the largest degree term was on the top. In the last one, we had a larger degree in the denominator, so the denominator was growing faster. So to kind of generalize what's going to happen here as x approaches infinity on rational functions, if the degree on the top and the bottom are the same, we're just going to look at the leading coefficients. All right, so going back to this example here, the leading coefficients were 6 and 10. We do 6 divided by 10, and that's where we got the 3/5. If the degree on top is smaller than the degree on the bottom, then the limit's going to be 0. So that's actually the third example we did. The degree on top was smaller than the degree on the bottom, so we ended up with a limit of 0. And then if the degree on top is larger than the degree on the bottom, then that limit does not exist, but it's going to approach positive or negative infinity. Now, I'm going to address this in another video, but we also need to consider what would happen if x is approaching negative infinity. And generally, we're going to have the same things happen. We just have to make sure we're careful about signs. In particular, we have to be careful about signs with any numerical values that we get and with infinity. If x were approaching negative infinity in this example, a negative infinity or a negative number squared is going to be positive, so this would still approach positive infinity. If we did some canceling and this was an odd exponent here, a negative number to an odd power is going to be negative infinity, so this could have been a negative infinite answer if x was approaching negative infinity. So we need to be careful about signs in problems like this.